Hello. Today we'll discuss something that was missing from the last lecture, the part 3 of the lecture about the AMC 12 year 2015 version B problem number 25. Specifically, it was why do we need vectors at all? So what is a vector? Let's read the dictionary definition of a vector. It says vector, a quantity that has magnitude and direction and that is commonly represented by a directed line segment whose length represents the magnitude and whose orientation in space represents the direction. Yeah, this is the most common definition that students tell me when I ask them to describe what is a vector. They say something that has magnitude and direction. But in a way, that is like saying a human being is an organism that has bones and living tissues. I don't think that is a sufficient description of a human being. So, what else is there? Well, let's look at this. Even this dictionary has more than just that. It says, 2, an organism that transmits a pathogen. So, from mathematical concept to an organism, okay? But it has more. 3, a sequence of genetic material used to introduce specific genes into the genome of an organism. So sequence of genetic material, in a way, it's not even an organism. It's a bunch of material, bunch of information. So there are really lots of definitions of vectors. In fact, there are lots of different kinds of vectors. So what might be a better way to understand vectors in general? Well, I'm sure there are exceptions, but one of the most useful ways to understand vectors is to think about this as something that has potential to cause some kind of change on something else, or something that is describing a potential change, whether it is in position or something else of any entity, even if the quantities we're describing, or maybe not in quantity, quality we're describing may be something that's not even a number. So, in our problem, how is this relevant? Well, let's discuss just a little bit more about the vectors. Most people, when they hear vectors, they expect me to do something like this and me to draw something that looks like an arrow that's like that, an arrow that's like this, and so on. This is a rather simple depiction because think about this, where this T represents time. So a vector, that is a function of a time. Well, I hope you guys all know what function is. Function is something that receives an input or something that where we have some kind of a controllable parameter and where we expect to see some kind of outcome that's always reliable. And often different input, different output. So different time, different vector. So different in magnitude, different in directions. And if we have two things interact with each other, yeah, they could cancel each other out in a way. Or they could add on to each other. For example, actually not for example, in two-dimensional space, we can represent almost everything in two-dimensional space in two fundamental directions. We usually call this horizontal directions and vertical directions. And we know that no matter how much you move horizontally, it's not going to change your vertical position. And no matter how much you move vertically, just the vertical movement or any change in the vertical itself will not be responsible for horizontal change. If you want to do a horizontal change, then you have to, force it someone introduced a potential for it to change horizontally, or somehow cause a horizontal change itself, or somehow describe it. For example, a vector of like this. We could think about this as moving horizontally this much, and then moving vertically this much. And the result is the same. Now, think about this as well. We could also describe the same situation by having something that moves up like that, and then making it be affected by something that causes this kind of change. So if you move up by this much, and if you move horizontally this much afterward, then you will do the same movement as this green vector. Now, for our problem, here is how it is stated. We have a B here. That was at the origin or at 0 spot. It moved east by 1 unit. So that's its first movement. And then it moved 30 degrees north and moved with a magnitude of 2. So that's its second movement and third movement and such. We could describe the situation in many ways. For example, let us assume that this is some kind of xy coordinate, which is what we used for number 1. Then we could describe the first position as a position vector 1, because we're describing as some kind of change in the position from the origin to this point. So position vector 2 will look like this. It describes the change of the position from here to here. Position vector 3. Then we could kind of break the whole situation up and say, then we could also think about each of these as a displacement vector. So this is my first displacement vector. We're describing as something that has a potential to cause a movement that is identical to this. And my second displacement vector will be this guy, which you could think about as, the difference between the second positional vector, so difference minus, and the first vector. Third displacement vector, we could think about this as a difference between the third positional vector and the second positional vector. And when you think about each of the displacement vectors separately, then we could think about our positional vector 3 as sum of the 3 displacement vectors. So we could think about a displacement vector from this B as something that causes the B's position to move, and depending on the number, depending on what is the situation. So is this the B's first movement or third movement or the nth movement? That displacement vector will look different. Depending on what the n value is, we have an evolving vector. We could think about each vector d1, d2, d3 separately, or think about this as a system of vector that can be described like this, or like these. So now, what is the easiest way to describe these displacement vectors for the B case? Well, in the B case, we could think about the first movement as moving purely with a size of 1 and the direction that's purely horizontal. It is here that a good way to express the whole situation is using the unit vectors. we could think about any x directional movement, any directional movement on x or any horizontal movement, and use something called the I as a unit vector. So I will be describing a 1 unit length of a horizontal movement or horizontal change. For the y, we could use the j. So j would describe 1 unit movement vertically. And then we could describe the situation as moving 1 I, and then since there's no vertical, our d1 vector could be described as this way. Since our initial position is 0, and since this is our first movement, our d1 vector also happens to coincide with our first positional vector. Now how about the d2? d2, let's think about what the problem says. The magnitude was 2. Its direction was 30 degrees up, so it was moving like this. So if we draw a right triangle to depict the situation, this is the situation we got. We have hypotenuse of 2, angle of 30 degrees. So the horizontal component is 2 times cosine 30 degrees. Vertical component is 2 times sine 30 degrees. And then, wow, 2, 2. We could put these things together and depict the situation as 2 times cosine 30 degrees in horizontal direction plus sine 30 degrees in vertical direction. D3, 3 times cosine 60 degrees, because if you look at the picture, now the angle is 60 degrees. Hypotenuse 3, we are right angle. This length is 3 times cosine 60 degrees. This length is 3 times sine 60 degrees. So horizontal movement of 3 times cosine 60 degrees, vertical movement of 3 times 60 degrees. So since those two both have to be used, then we could actually generalize the case. For n's displacement, we can say dn has magnitude of size n. And this direction is, well, 30 degrees, 60, so 0. And here we could think of 1 as cosine of the 0 degrees, and the 0 as sine of 0 degrees. So that as cosine n minus 1 times 30 degrees in the horizontal direction, and sine n minus 1 times 30 degrees in the vertical direction. So we can describe the whole motion using vectors, using where this vector d is described by this relationship. And the vector d, as the n changes, will be evolving in the following way. And it is this portion, the portion that I keep writing in the parentheses, where since I did not want to write everything like that, I introduced a phasor notation from electrical engineering, where this phasor notation is defined as angle theta is equal to cosine theta times in the horizontal direction plus sine theta times the vertical direction. So this whole thing is a shorthand for this unit direction. By the way, if you think about the size, the length of this vector, we can see the following. For an arbitrary angle, so let's say our theta is something like 120 degrees, then it doesn't matter. That thing will have horizontal direction, so if 120 degrees, then it will have negative cosine negative direction. So you can think of this thing as moving to the left at the size of cosine 60 degrees or 1/2. So again, let me actually do that. So picture of this situation will be like this. Here is our reference direction. That's 120 degrees. If you want to know the size of this thing, again make a right triangle out of the whole thing. Size of this will be equal to cosine of 120 degrees, which is negative of, the magnitude will be same as the cosine 60 degrees, which is 1/2. Magnitude of this part is sine 120 degrees, which is square root of 3/2. But more importantly, no matter what the angle is, the size of the hypotenuse would be square root of the bottom side square, cosine squared, plus vertical side squared, and this thing by Pythagorean identity will always be equal to 1. In other words, this one is considered to be a unit directional vector that describes only the direction that this vector is pointing to, and not really describing the magnitude, because it has just size of 1 unit, and that 1 unit can be anything, and if you multiply that by a number, then of course that number will dictate how big your actual vector is. So going back, we are trying to say, since our d of n, I just erased it, but since our d of n describes a situation where it is a difference between our current position and the position right before it, our p of n, our combined position would be sum, I need to use something else, sum of k equals to 1, the sum of the first displacement to the nth displacement vector. And vector summation, you can think about that as no matter where you are, since all it matters is how much horizontal and the vertical movement there is. Doesn't matter where you're located, as long as you make it act on the same thing. We can make it act on the origin. So every vector will be acting on the origin. Every displacement vector will be acting on the origin, which is the why I am drawing picture. I drew a picture that looked like that. I need another arrow here. So this is the background for me using these pictures to do the part 3. And now let's think about just one more thing. I kept saying this is horizontal, this is vertical. What else do we know in mathematics where no matter how much you change in something, the other part doesn't change? Of course, by me saying other part, that means that we are describing something that has 2 parts to it. What kind of number we learned in mathematics actually has 2 parts to it? It is the complex numbers. Complex numbers is a number that has a real part and an imaginary part. Wait a minute. And in fact, if anybody is in electrical engineering, electrical engineers will probably write it as J. J? Now, this is a real part, that's an imaginary part. No matter how much you increase or decrease the imaginary part of a complex number, it's not going to affect the imaginary part. And if you add two complex numbers, then real part will only affect the real part, imaginary part will only affect the imaginary part. Just like when you add two vectors, horizontal parts will only add the other horizontal part to give you some of the horizontal change. Vertical parts will only add to other vertical parts to give you some of the vertical change. So it is possible to depict this vector as a complex number in a complex plane. Complex plane, real, imaginary. That looks a lot like x and y that we usually use. So this is the motivation behind why we should explore using complex numbers to solve this problem. And as the luck have it, because there exists a convenient mathematical identity that actually takes care of this in complex number, we have something that no longer requires me to draw lots of complicated pictures. So see you next time.